taught in a completely unsupervised way, and both of these papers have been doing that. Once you've learned those senses, you can visualize them using the same kinds of tricks that we've been showing before. By the way, I think none of us here has mentioned it, but the way we get these lower dimensional visualizations of word embeddings is using nonlinear dimensional reduction. So the algorithm that I use and many people are using is called TSNE, T-S-N-E, and it's very easy to use. There's existing code up there. You don't have to understand the details. You just plug it in. You give your high dimensional representations, and out you get two-dimensional or three-dimensional representations that you can visualize very easily. Other kinds of applications that have been pretty successful, we've seen a bit of that at the beginning of the tutorial in acoustic models where you're trying to predict phonemes given a window of acoustics. This work was led by people in Toronto, Mohammed and Dal and Hinton in particular, where they obtained state-of-the-art results on timid, which is an old phoneme level classification problem. And this has been improved and extended and mixed with a language model to obtain state-of-the-art results that Chris mentioned at the beginning of the tutorial at Microsoft that has been released for their system, their speech recognition system for audio and video indexing. So here's another, this is the last application I'll be doing, which is domain adaptation for sentiment analysis. So we've seen already applications of sentiment analysis. In this application, we consider a particular situation where we want to do sentiment analysis on a large number of domains. So here there are 25 domains, things like videos and books and music from Amazon, and we want to be able to generalize what we have learned on some domains and apply it on new domains for which we haven't seen any labeled data. So it's a pure domain adaptation task. And so we use here a denoising encoder with sparsified rectifier units as our unsupervised pre-training, and then we just apply an SVM on top of that. Actually, we stack several denoising encoders. So this is the quality of the transfer, so the smallest is the better. For different methods, the state-of-the-art here is SFA on that data set, and it gets about 1.3 something. The transfer ratio, we go down to 1.1, and 1 would be sort of the theoretically optimal, saying that on the new data we're doing as well as on training domains. A nice, interesting observation on these models is that the features that are being learned in a purely unsupervised way seem to disentangle various components of the distribution. So some features specialize to domain, whereas other features specialize on sentiment, which is very useful. And imagine if a model was able to do that perfectly, it would be very much easier to classify sentiment for domains from these than from the raw data. Okay, let's move to another part. Briefly, some pointers. First of all, related tutorials. I wrote a Scholar PDF entry for neural net language models. Then there is a series of tutorials for the deep learning tutorials that use here that actually are with Python code that you can use to play with some of these methods. These are not specifically for NLP, but there's kind of good tutorial material. Then there's the Stanford deep learning tutorials with some simple programming assignments, which you can have a look at. There's a recursive encoder class project that's connected to what Richard has been talking about. And then upcoming, there's a graduate summer school starting next week on deep learning and feature learning, for which I suppose material will be posted as the summer school proceeds over the course of 3 weeks in July. Then last week at ICML 2012, I gave a tutorial on representation learning. which you can find here. By the way, I'm not sure if all of these are on your printed versions, but all of the last minute updated slides are available on the web. If you go to any of our web pages, Chris, Richard, or mine, you'll find a pointer to the latest version of the slides, as well as references to the papers that we're citing in a separate PDF. So that would be useful if you want to follow up on this. Here are also some pointers to software that's relevant. So I mentioned the deep learning tutorial. They use a library called CNO that's essentially in Python and does automatic differentiation and compilation of symbolic expression to CPU and GPU, so that can really allow you to speed things up. Then something that can be very interesting for fewer users of NLP is the program called Senna by Colbert and collaborators, which does part-of-speech tagging, chunking, name entity recognition, semantic labeling, and parsing. You get state-of-the-art performance on these tasks. Interestingly, it's very fast code. It's very short, 3,500 lines of C. Uses very little memory. It's very easy to use. So you can have a look at that pointer. Then I mentioned pretty strong results obtained with a recurrent neural network on GitLab. You can also get this code from this web page. And finally, you can also get the code for the recursive neural net and the recursive autoencoders from Richard Selcher's web page. Now, speaking about software, I think there's still work to do from people like me and Richard and Chris and others to make the deep learning algorithms really easy to use for non-specialists, in particular NLP. This kind of thing has been really important for SVMs, thanks to off-the-shelf packages. Lots of people have been using SVMs without having to understand the math behind SVMs. And we need something similar for deep learning. There are already some pieces out there, and I've given you some pointers. But it would be nice to build off-the-shelf NLP classification packages that use deep learning and are very generic, using only raw text as input, as well as possibly labels for label data to help solving particular tasks you're interested in. All right, so now we have a bit of time to talk about sort of practical aspects of training deep learners. So here's a bit of publicity to go a bit further than I'll be able to do in the next few minutes. I've just written this paper, which is going to appear in the book. And the subject of the book is going to be tricks of the trade for neural nets and deep learning. And my chapter is called Practical Recommendations for Gradient-Based Training of Deep Architectures. So it goes through many of the things we talked about already, like the unsupervised pre-training trick. The very important point of how you do stochastic gradient descent and set learning rates. Probably the most important thing to understand when you want to use these things in practice. It's very simple, but you really need to get it right. And it talks about the many hyperparameters that are involved in training these things. So, for example, the learning rate, you may want to anneal it, to reduce it gradually. So that's the idea of the learning rate schedule. There's the idea of early stopping, which is that you can decide on the fly when to stop training in a way that's also regularizing automatically. The idea of mini batches, in other words, making changes after something like 10 or 100 examples rather than after each example to take advantage of GPUs and multiple machines. How to initialize parameters, how to initialize weights, how to set the number of hidden units, how to set regularization coefficients like L1 or L2 weight decay, make the weights, the parameters closer to 0 somehow and possibly 0 in case of L1. How to use sparsity regularization on the activations, on the representations themselves. Some tricks or some ideas that how to improve the debugging, for example, using a finite difference check of the gradient, something really simple and very useful to guarantee that your code is doing the right thing. And then something really practically important, because we have all of these hyperparameters, people sometimes are scared by these methods. It's, oh, okay, there's so many buttons, I'm not an expert, so I can't really use that. But actually, there are ways to automatically set hyperparameters, and we discussed that in this paper, and point to a longer paper that just appeared this year by Bergstra and myself. And the idea is to use random sampling to search in the space of hyperparameter settings. You do need like a cluster or a multi-core machine, but many people now have access to these kinds of resources. And with that, you can pretty much automate the search for hyperparameter values. So one particular question we get asked is, well, what kind of nonlinearities we should use? So we've already seen the sigmoid. It was one of the first kind of nonlinearities people explored from neural nets. The hyperbolic tangent is very similar. It's just a scaled and shifted version of the sigmoid. And it just happens to be centered around 0, which gives it numerical advantages. And that's what you find in most papers using these things. But more recently, different variations have been proposed, and in some cases work substantially better. For example, Colabert has been using the so-called hard tanh, which is like a piecewise linear version of the tanh. And we've been playing with something called the soft sine, which is smoother than the tanh and leads to less saturation of the units. In other words, the nonlinearity is smoother, doesn't go to 0 exponentially, but linearly. And then this really simple one called the rectifier, which is just max argument 0, which actually works quite well for natural language tasks. So these ISTATS paper actually talk about this rectifier nonlinearity. Let's say a few more words about stochastic gradient descent. The idea is simply that we're going to modify our parameters by subtracting the gradient times a scalar, which we call the learning rate. The gradient is the derivative of the loss for one example or a mini batch of examples with respect to the parameters. So most important thing I should say is don't use so-called ordinary gradient descent, which here we replace this gradient by the sum of the gradients over all your training examples, because that would be really, really very slow and useless. You should use either stochastic gradient descent, possibly with mini batches, or second-order methods like LGFGS or conjugate gradient. What we can observe is that when the data set is very large, stochastic gradient descent wins over all pure batch methods that require summing over all the examples. But recently, people have proposed large batch LGFGS. So instead of having to wait seeing all the examples before doing an update, which is sort of the theoretically correct way to use these methods, you cheat a little bit and you use a small number of examples, like 1,000 or 10,000, and then you do an LGFGS update. And that actually works well. In the case of stochastic gradient descent, the most important hyperparameter is the learning rate. This coefficient you put in front of the gradient. So there's a very simple recipe if you don't want to complicate your life. Just keep it fixed. Use the same value for all the parameters. Now you can get some improvements using different recipes that allow the learning rate to change over a number of iterations, but also for different parameters in your model. So for example, Colabert scales the learning rates by inverse of the square root of the fan of each neuron, and he has some motivation for this. There are also theoretical motivations for letting the learning rate decrease, for example, in 1 over t, where t is the number of iterations. In particular, this gives you theoretical conversion guarantees. So one particular variant that we use that works quite well has two hyperparameters. The first one is the initial learning rate, and the second one, this far, is a time constant. So when the iteration number is less than the time constant, this is just epsilon 0. So we initially have a constant learning rate, and then when t equals 2 tau, you're going to have epsilon 0 divided by 2 as our learning rate. After t equals 3 tau, we're going to have epsilon 0 divided by 3, and so on. So you can see that the learning rate goes down in 1 over t, but is initially constant, which is nice to hear. Now regarding recurrent nets in particular, and constantly recursive ones or very deep networks, there's an analysis that I've done in the early 90s, which is important to understand, and explains some of the difficulties that people have had in training very deep nets and recurrent nets. And the difficulty is that if you look at the gradient with respect to some internal state, like you can think of this as scaling units at stage t in a very deep net, or at time t in a recurrent net, you can decompose it as the product of a bunch of Jacobian matrices. Jacobians are matrices of derivatives, where each of them tells you how the state at time t plus 1 relates to the state at the previous time step. The problem is when you multiply many matrices together, and actually you have a similar shape and similar kind of values, it's like, you multiply a bunch of numbers together. As you multiply more things together, this will either tend to go to 0 or to go to infinity. And so your gradients can either blow up or vanish. And many people have been discussing this. And it turns out that there's a very simple trick that addresses the problem of when the gradients explode or become too large, which is clipping them. That has been introduced by Nicolas again. It's a very simple thing. When the magnitude of the gradients is above some threshold, you clip it to that threshold value. Parameter initialization is also quite important because we've seen that there are local minima, and you have to be careful about how you initialize those models. Now, for the biases, these intercept parameters, actually you don't have to worry about them. You can initialize them to 0, except for the outputs or the reconstruction units, where there's a better recipe, which is to initialize them to their optimal value, assuming the other parameters were 0. In other words, the first thing you do when you before you start training is you predict your class probabilities optimally if you were to ignore the input. Okay, so that's kind of the easy part, initializing the biases. Then initialize the weights of all the layers. Typical recipe is to sample from a uniform from minus r to r, and the question is how you choose r. You can also use the Gaussian, but I prefer uniform because you're guaranteed not to have large values in this way. So the way you should set r logically is that it should be smaller when there are many weights that are involved, that are summed together into a unit. And so many authors have proposed that it should go into something like 1 over the square root of the fan-in, which is the number and the size of the previous layer. But we've done some analysis suggesting that actually it should also depend on the size of fan-out, in other words, the next layer size. So if you're looking at the weight matrix between one layer and another layer, you should take into account the size of the 2 layers, and here's sort of a recipe for the case of Tanch unit, and you just multiply this number by 4 for sigma units, and the analysis is in this AI stats paper. And using this kind of analysis also tells you that for learning initializing embeddings, you should use something like r equals 1. Okay, last part of this tutorial, a little bit of discussion. Many people who approach deep learning have concerns, so let's try to address some of these. One concern is that, oh, there are so many algorithms and variants, what should I do, what should I do? Well, okay, it's apportioning fields, and there's a lot of exploration, there's a lot more that can be done. But some of the methods are becoming standard, and the code is out there, so I wouldn't be too worried. It's actually a good thing. A more serious concern is that there are many hyperparameters. In regular, in things like linear models or SVMs, typically you have one or two hyperparameters, and so you can just set it by hand, by trial and error, and you don't have to worry too much about these. If you have 2, 3, 4 hyperparameters, then exploring by hand all the configurations just becomes impossible. Fortunately, you can use this trick that I was mentioning before of random sampling to automatically set hyperparameters in a way that's quite reproducible and efficient. And you still need to maybe launch dozens or even hundreds of jobs, but nowadays it's not so hard anymore, and if you use GPUs, that's even faster. One thing you have to realize is as soon as you consider a space of models that's richer, more powerful methods, then you're likely to end up with more hyperparameters. In a sense, exploring hyperparameters is like exploring the model space. One thing you can do to reduce the number of hyperparameters is replace stochastic gradient descent, which has one or two hyperparameters, by things like LBRGS, which also has one or two hyperparameters, but they are less sensitive. You can kind of use default values and